Molly with NASA 360. Thank you so much for joining us. We are joining you live at NASA Langley's Research Center in their hangar. And though, if you can see behind me, it may not look much like the surface of Mars, but teams have traveled from different universities all over the country to compete in this really exciting new challenge called the RASC-AL Mars Ice Challenge. And as you can see, teams are busy setting up these drilling systems. And what these drilling systems are going to do is, I think, revolutionary. They're actually going to use these systems to drill through subterranean Mars surface matter and hopefully be able to harvest water from these large ice deposits that we found on the surface of Mars. So teams have gathered from all over the country to participate in this. They're from some of the main universities that you know and have heard of. And we'll just take a couple more seconds for folks to join in with us as we get settled here. I'm going to actually turn on my Facebook Live here so I can watch you guys and answer any questions that you might have. So weird to see myself there. Thank you guys so much for joining. If you have any questions today, please feel free. I have it pulled up here. Hi, Powell. Hi, Gabriella. Thank you guys so much for joining us. This challenge, just to answer some questions as everybody gathers, is called the RASC-AL Mars Ice Challenge. And so teams are competing with these drilling systems that you can see behind us. And these drilling systems they've designed to drill through the simulated surface of Mars and tap into these large ice deposits that we found on the planet and hopefully be able to sustain water from these, and that would be usable water. And the implications of that discovery obviously are huge. In just a second, we're going to speak with Chris. He's an aerospace engineer, and he's in charge of the steering committee. And we're also going to get a chance to talk to some of these teams and see what really sets their systems apart from the competition. Hopefully enough to let them win this challenge. We'll be doing live streams over the next 2 days, so be sure to tune in to those as well. They'll be at 11 a.m. on both days, tomorrow and on Thursday. And I think everybody's ready. If you guys are ready, you want to go talk to Chris? Let's go learn more about this challenge and see, hey Chris, and see what this whole thing's all about. I mean, the challenge itself sounds so cool. Anybody drilling into ice on Mars, I mean, you have my attention, but I'm sure it's more than that. What's this competition really about?
Well, the reason why we're here is because Mars is hard. It's hard to get there, it's hard to land there, and it's hard to live there. The reason why it's hard to live there is there's a lot of things that are missing that we have here on Earth. It's very cold there, there's no atmosphere, and more importantly, there's not any easily accessible sources of water. So what we've got the teams looking at today is a way to acquire water so that someday when we go and send people to Mars, they're able to get the water they need to live on, to provide oxygen to breathe, even to provide the rocket propellant they need to come home with.
They may want to come home, they may not, you never know.
Right, but whether they're staying there for a few days or a few years or the rest of their lives, they're going to need water, and we're trying to find out the best way to get it for them.
So walk me through all the action that's happening behind us.
So this is day one of the competition. The teams have just arrived and are starting to set up the equipment they're going to use. Now, you'll be able to see as we're walking around and looking here some of the drilling setups and some of the other concepts they're looking at. They're going to be set up above these blue coolers, which are essentially stations that are simulating the surface of Mars. Now, we can't quite do a full simulation here. It's a little bit hotter in a 90-degree hangar than it is on the surface of Mars, and we still have some air pressure so everybody can breathe. But at the same time, we've got a lot of the levels here we need in order to simulate subsurface ice, and then these teams are going to be attempting to drill down into that and pull out the ice and melt it into water for us to use.
That seems really difficult to do.
It is. We had over 30 teams apply, and we've selected the best 8 concepts here, but these teams have been putting in effort for a solid year to get these concepts ready to go, working day and night, hours upon hours on end here, and they've built some pretty impressive looking systems here. These things weigh as much as 50 kilograms, they can be a couple of meters tall, and they're going to have to ultimately show that they can operate them without human intervention. That's the real challenge here, because it'll be a while before we can send people to Mars, but before that, we'd love to be able to extract the water without humans having to be right there in the loop.
Sure, that makes perfect sense. As you can see, there are so many teams out here that are competing. It's really fun to see so many young people. I mean, these are all university teams, and this is a really difficult challenge. So as I understand it, the systems that they've built were designed to work on Mars, but then they had to tweak and modify them for functioning here on Earth. Is that right?
That's correct. So the papers that they've written with these describe how these concepts would work when they actually got it in the environment on Mars. For the demonstration here, we've asked them to then modify their systems so that they're able to test them here on Earth. But ultimately, we want this to be a way to find new innovative concepts that we can leverage when we do actually go to Mars.
Verizon from our live stream wants to know how the system will be powered on Mars.
So we're looking at a couple of different concepts for how we'd actually get power on Mars. Depending on where you are on Mars, solar power might work out pretty well. A bunch of solar arrays, some batteries to store energy and run you through the night, and then you'd be in good shape. On the other hand, you might just need enough power that you might have to send a nuclear power system. That then would involve bringing one or a few small nuclear fission reactors and using the electricity from that to keep your systems going day and night.
What are some of the other challenges that teams run into with this actual competition? It's so difficult.
Sure. So they're doing this on, while they're taking classes, while they're doing other work, while they're, trying to prepare for a job, whether it's at NASA or industry or somewhere else. And they're having to do it on a fairly limited budget. They received a stipend from NASA. They've been able to hopefully get some funding from some other sponsors and such. But at the end of the day here, they're not getting to work on a multi-million-dollar project. Instead, they're really doing this through a lot of blood, sweat, and tears.
Right. For those of you that are just joining us, we're here at the NASA Langley Research Center in Virginia, and we're covering the RASC-AL Mars Challenge, which is various teams competing with these drilling systems that they've created as they prepare to drill through the simulated surface of Mars and tap into large ice deposits that we found on the subterranean surface of Mars. And I'm talking to Chris, who's an aerospace engineer, and along with the steering committee here in this challenge. Chris, what do you think, what do you hope is the biggest takeaway that folks take away from this challenge in 2 days?
Well, for the students here, I'm hoping it turns out to be a great experience for them to understand what it means to try and design a system that could eventually be used to go to Mars. For those of us in NASA and industry who are helping putting on this competition, we're really hoping to see some cool ideas here that we can then leverage in our future mission planning that will help make it easier when we want to send humans to Mars. So really, we're hoping it's a win-win both for the students and for NASA.
I think it will be. So walk me through this blue container, because this is the housing cell for the drilling challenge, right? Yes.
So what we've got here is at the top, we've got the lid to what's essentially a commercial fishing cooler. This is containing the ice we've put in there and keeping it cool, even though it's rather hot here in the garage. As you can't see right now, but right below, we've put in about 18 inches of simulated Mars soil. We've mixed that out of clay and gravel, and that's had a chance to kind of freeze over from when we built it yesterday, so they're going to be somewhat simulating the conditions of the soil on Mars. And down below that, there's then 6 layers of ice blocks. We've got 2 large ice blocks that together make about 18 inches in height of ice, and all around it is styrofoam and dry ice to help keep it cold over the course of the competition. So the goal is that teams systems to the top here, drill or dig or others work their way through the regolith to the ice, and turn it into one of these buckets.
It sounds easy, and I'm sure it's not. Chris, thank you so much for talking to us. It's really interesting to hear your take on everything, and I'd love to go meet some of the teams, don't you guys? I think I might take a little walk.
Great. Thanks, Molly.
Yeah, you guys want to come this way? This is what's called the pit. So since this is the testing day, this is when all the teams have traveled in. They are unpacking these drilling systems that they've spent a year figuring out, tweaking, putting final touches on, and then have one day to get them here, assemble them, make sure nothing is wrong, make sure that there's nothing that needs to be tweaked, make sure everything's working properly. But let's go talk to one of these teams over here and see how their system is coming along. Hey guys, how's it going?
Good, how are you?
Your system looks pretty darn good.
Thanks. We tried to base this off of a mining and petroleum industry standard where you actually use an injection oil. Only in this case, we're not injecting to cool the drill stem, but actually to melt the ice underneath the Martian regolith that we're supposed to be drilling through. And once that ice has been melted, we actually pump both the water and the oil back up through the hollow drill stem and into our separation tank over here. And then from this separation tank, we are able to separate our oil and water out into 2 different levels. and the water gets pumped into a final storage facility, and the oil actually gets recirculated back through the system. So, yeah,
Seems like there are a lot of areas that could have error.
We have tried in all instances to mitigate the possible points of failure. The part of that has come in with our control system. Rather than having multiple computers control this robot, we've actually all opted to have everything run through one Raspberry Pi, and that has allowed us to minimize those that kind of electronics aspect points of failure. As far as like not being able to drill through the regolith itself, we have a plan in place that if we hit any kind of strong resistance or anything like that, we can back out and go to a different location. That's one of the things that the 3D printer kind of designed for our movement in the X and Y directions allowed us to achieve, is that flexibility.
Is that why you ultimately went with this design over maybe some of the other prototypes that you were considering?
Yes, and that's also something that for a future path to flight for going to Mars, you could actually eliminate the X and Y system entirely and instead plug that into a rover-based system that would allow you to have the freedom to move not just within a 1 meter by 1 meter area, but wherever you had a deposit located near your settlement.
Aside from the winning aspect, which would be very nice, what would it be like, what would it feel like to have this technology on the surface of Mars one day for you?
That would probably be one of the proudest moments of my entire life, would be to have that happen, to know that this team was able to contribute to the furtherment of human colonization of space. I don't know. Maybe having children and my marriage to my wife would be the two things that would top that.
Say that first, quick. Say that first.
Sorry.
That's awesome. And wouldn't your team one more time?
We are the In-Situ Resource Exploration System, also known as INRES, from West Virginia University, and we were sponsored in part by the West Virginia Robotic Technology Center, which works through us and parts of NASA to help facilitate and develop future technology.
Awesome. Well, good luck. We'll be here over the next 2 days. This, again, is just the testing day for these teams. I'm going to take another little walk. You guys are welcome to join. But we will be doing live streams each day, tomorrow and Thursday at 11 a.m. Eastern, so be sure to tune into that. I'm doing my best to be on the phone and try and field your all's questions, but if there's anything that you want to ask, there will be 2 more days that you can continue to ask questions. I apologize if I miss you. But again, this is the Mars Ice Challenge by RASC-AL. And so teams are using all of these different drilling systems, if you're just now joining us, to hopefully one day drill through the subterranean surface of Mars to collect water from the large ice deposits that are there on the planet. So we're looking at some of these teams as they get set up today. And we're going to go talk to another team. This team is actually from Colorado, the School of Mines. And it's just really fun to see all of the different systems that have been developed here and to see the different approaches. They all look somewhat similar from far away, and then once you get up close, you can definitely tell the difference between design. Hey guys, you all have a second? Can I pull you away? Yeah. I just wanted to kind of hear more about your system and why you all chose to design it the way that you did and what your hopes are for this week.
So we started back in September when the competition was, and we worked to design for 4 months and submitted our proposal and saw what happened, and sure enough, here we are. And had a lot of design changes, a lot of lessons learned about taking a project from really start to finish and learning about how to purge its materials, integrate them all together, and really make the system work, and navigating team dynamics along with that as well. So it's been a great experience, and we've learned a lot.
How many of there are you? Is it just you 3?
Us 3 traveled.
Okay.
A team of 9.
A team of 9. Okay. I was going to say, good grief. Yeah. That's wonderful. So what is it that sets your all's system apart from maybe some of the other teams competing?
I would say that we have a pretty simple design. We wanted to make it something that was executable but also effective, and I think we really pulled through on that and made a system that should do its job well, and but that has minimal moving parts, and the things that we have implemented are definitely effective to get their job done. I guess another key design is our casing as part of our, which goes around our auger. That is a more unique design, and you can see it over there, and that allows us to really get into the dirt well. And
I might take a second. We can show that auger in just a second while I answer some questions from our Facebook Live folks. Let's see here. Donnie Hudson wants to know, will the drills be stationary or mobile? You can probably answer that one.
Yeah, sure. So while the drill is drilling the hole, it'll be in one place as far as the actuators go. Once we've completed one hole, though, we'll move it, translate it on the horizontal, and then drill our next hole. So, yeah.
What do you think is going to be the trickiest part of this challenge for the drill?
I think we faced some challenges with setting our casing and making it to where we can actually get ice, come up that's not mixed too much with the dirt. So I think that'll be a little bit of it could be tricky to navigate in some ways, but I'm also very confident in our design and that what we have will work.
Can you explain that system a little bit for folks that may be joining us for the first time? This is the RASC-AL Mars Ice Challenge, and so teams are using these drilling systems like you see behind us to drill through the surface of Mars, through the sediment layer, into the ice that's located in these large ice deposits on the planet. But it's not just water you're pulling out. You have to actually get clean water.
Right, and honestly, I think our team lead, Justin, would do a better job of explaining. This is more of his subsystem, I guess, than mine.
Hey, Justin.
So we're using an auger. Liquid water is not typically stable, or water is not typically stable as a liquid on Mars, so you have to use a dry cuttings removal system, which is different than we use here in the petroleum industry. So we've chosen an auger, and the important thing with the auger is we need a casing to segregate the soil from the ice as we're penetrating through the test bed. So I guess the first contact that we make is clay, and we're going to drill through that. Here's the casing, here's the auger. So all of this is going to penetrate, and once we hit the surface top of the ice, the weight on bit experienced on the casing won't allow the casing to continue, but the auger is going to continue into the ice. So we'll reach our target depth, and at that point the ice will act like a consolidated wall. So we'll have ice on our flutes wrapping around the auger. We can pull everything back up above surface, and then we translate a box underneath with heating pads, heat it, and then transport it as a liquid.
When you first heard about this challenge, what were your initial thoughts versus what you've learned now, looking back?
I think just the environment is so hostile on Mars, and like I was talking about earlier, the low atmospheric pressure really changes how we're approaching this, and we can't use literature that's been studied and practiced here on Earth because of that. So definitely making it applicable for Mars, but also proving that concept, testing it in the Earth atmosphere has been a huge challenge for us.
Well, I wish you all the best of luck. We'll be following their progress over the next 2 days. You can tune in live on our live stream at 11 a.m. And we're going to talk to Chris one more time in case anybody missed it earlier. Chris is an aerospace engineer. He's in charge of the steering committee for the program here. Chris, I found you in front of this very, very pretty sign. It must mean something.
Well, it does. We're doing this as part of Langley's 100th centennial. So it's been 100 years since the Langley Research Center opened up, and now we've got this challenge here that we're doing as a part of it, and it's part of the RASC-AL set of competitions that we've done for several years now. What we've got these teams doing is they're coming in and showing us how they might go about getting ice from, well, not the real surface of Mars, but at least a simulation of the surface of Mars that they could then turn into water that someday we would be able to use on Mars, because Mars is kind of a hard place to go. It's very cold, it's very dry, there's not a lot of air you can breathe, and we're going to need water if we're going to live there.
That makes a lot of sense. What are you hoping that, aside from the team that wins the challenge, what do you hope are the takeaways from this challenge?
Well, I think every team gets the opportunity to see how to tackle a really tough design challenge and how to come up with a concept that they can use that's relevant to being able to go to Mars. On the NASA side of things, we're really hoping to see some ideas here that we could eventually use someday for our future missions when we send people to the surface of Mars. So really, we see it as a win-win for both the students and for NASA and industry.
And we're clearly today here at NASA Langley. They may think, man, that looks awesome. I want to do a competition like this. I want to join a challenge like this. How can they get involved?
Well, I'd certainly encourage them to take a look at the RASC-AL website. It's at rascal.nianet.org, and we can put that on the NASA 360 page later for people to look up and find. We usually try and host a couple of challenges each year that give students an opportunity to design ideas that can someday support us. One of the ones we had years ago actually led to a drill concept that is now being flown on the surface of Mars. So we went from an idea that was developed by students to actual hardware that's on another planet. And someday, some of the things you see here today might follow that same path.
Just a couple questions from our live stream audience. They're wanting to know, is the water on Mars drinkable? Which is a great question.
Probably not when we first get it. You might be able to hear there's a... We're right next to the Langley Air Force Base, so you can sometimes hear the F-22s go roaring over.
Yeah, this is the green screen here.
Yes, we are next to a working Air Force Base, and here they come again.
Awesome. So for any of you joining us here, we're center and we're talking about the RASC-AL challenge here with Chris, and we're asking the question, is the water on Mars drinkable?
So when we first get it, probably not. There will be a lot of other minerals and salts and frankly some pretty dangerous chemicals dissolved in it. So in addition to the challenge of getting the water, we're also going to have to process the water into a drinkable form. But that will be part of the challenge not being looked at today, but part of the challenge that NASA has to solve and industry has to solve going forward is how to turn that water into something that's safe to drink.
Do you think at your age, when you think back to your time spent at university, that you would have been able to take on a challenge this difficult?
Whew, it would have been tough. I think maybe with a really good, strong team, like a lot of these universities, really all of them appear to have, maybe. But I tell you what, this is a really good challenge here because it's asking them to solve the kind of problem that we at NASA don't yet know exactly how to solve. So we're hoping that some of the innovative ideas that they can come up with are eventually going to enable us to actually solve the problem.
And then I know this is a test day, but my last question, what kinds of things are you hoping to see over the course of these next 2 days? We're going to be doing live streams every day at 11 a.m. Eastern if you want to join us. But what kinds of things should we be looking for? What are the problem areas? Where's the action going to be?
So the real action comes tomorrow and Thursday when the teams are actually drilling. Tomorrow they get to be very hands-on with their system, trying to make sure it works the way they want it to work. Then Thursday we're going to up the challenge for them and ask them to do this like it would have to be done on Mars without any direct human intervention. Instead, they're going to have to rely on automation and computer programming to help their systems run. Now, we're going to give them some extra points for however much water they can collect in that more difficult environment, but we'll see how the challenge goes. I'm really excited to see what they can do, Molly.
Well, as you can see behind us, they are busy utilizing this test day for as long as they can. We will continue to cover this event here over the course of the next 3 days, so please be sure to tune in live. If you have any questions, please utilize the live stream. I'm trying my best to keep in touch with all of them, but we love when you're involved. We love when you send us questions, and hopefully we'll see you tomorrow, 11 a.m. Eastern. Be there.